everyone, I am Abdel-Rahim MEZIDI, a PhD student at the Laboratoire Bercurian, and I'm glad to be here to present our work titled Bregman Proximal Viewpoint on Neural Operators. So basically, this can be summarized in two main contributions. First, a new framework where the training of neural operator are seen as a bi-level optimization problem. And then the conception of a new family of architecture arising from this framework. But before we dive into this, let me present you neural operators. So contrarily to neural networks, which are able to learn mapping between vector spaces, neural operators are able to learn mapping between function spaces. So they take as an input a function A and give as an output another function U. For example, they could take as an input the velocity field at an initial time and give as an output the velocity field at a future time. For example, like in the Navier-Stokes equations, or they could take as an input the porosity of a material and output the velocity field of a fluid passing through this material, like in the Darcy equation. So neural operators are very interesting, specifically when we work on a physical phenomenon governed by PDEs. And now let me present you the basic architecture of neural operators, which is composed of three main elements. So first we have a layer P, which will take the input and lift it into a higher dimension. Then we have a succession of T operator layers, which I will explain more later. And finally, a layer Q that will project back into the output dimension. And in order to explain a bit better the neural operators, I'm going to take the example of the most famous model, which is the Fourier neural operators. So as I've said, we want to learn a mapping between function spaces. And in order to do that, we need to have some basis to express these functions. And the easiest way to do that is to use the Fourier basis, which led to the development of Fourier neural operators. And as you can see here, the only difference is that we have here T Fourier layers. So let's focus on one of these Fourier layers. Each and all of the Fourier layers will share the same architecture. So on the first branch here, you will take the input and apply the Fourier transform. Then you will apply a linear transform on these Fourier modes. And finally, apply the inverse Fourier transform. And on the other branch, you will apply a linear transform in the latent space. And after a summation here, we will apply an activation operator sigma here. An interesting thing to see is that here we are doing a linear transform in the Fourier space. So we could consider that this whole branch can be considered as a convolution. So we apply a convolution in the whole image here. So we can generalize this architecture by replacing f and f-1 by u and u-1, which are just a unitary operator and its inverse. So for example, if we do Fourier, then we have the Fourier neural operators. And if we use the wavelets transform, then we have the wavelets neural operator. So generally, we see the output of such layer as a parametric operator on the input. And the first contribution is to view the output of each layer as the solution to an optimization problem depending on the input here. More specifically, this optimization problem is composed of 4 elements. First, we have FT, which express the relationship between the output and the input in the operator space. Then GT, which express the relationship between the output and the input in the latent space. Then here, divergence T, which is just a generalization of kind of distance. For example, Euclidean distance is a divergence. And this divergence will impose that output and the inputs are close to each other. And finally, regularizer H, which is just impose some regularity on the input. And before training, we will have to choose and fix our divergence D and regularizer H. And we'll see later that their choice are very important to the choice of our activation function here, sigma. And we'll try to learn and train our parameters FT and GT. But now, in order to retrieve neural operator architecture, we need to impose some constraints on these components. More specifically, if FT and GT are bilinear, if D is a quadratic distance and H is a convex function, then we are able to find a closed form solution to this problem. And we also have some equivalences here. So the gradients of FT and GT will be equivalent here to our linear layer RT and WT. And our activation operator here will be equivalent to the proximal operator of H. So our proximal operator is basically a generalization of a projection with an additional penalty. And with these equivalences, we are able to retrieve the neural operator architecture here. But now, if we impose some different constraints on these components, we are able to create new architectures. More specifically, if D here is not a quadratic distance, but a Bregman divergence, then we are also able to retrieve closed form solution, but with different equivalences. So we still have here the gradient of FT and GT equivalent to our linear layers here, RT and WT. But now our activation operator sigma is equivalent to the proximal operator of H with Bregman divergence. And we also have here a new branch, very similar to ResNet, which involves here sigma minus 1, which is the inverse of the activation operator, and it is closely linked to our Bregman divergence. So we call this new architecture Bregman neural operator. An interesting property of this architecture is that when our linear layers here, RT and WT, are equal to 0, our output here will only pass through this branch, so sigma minus 1 and then sigma. So the output of this layer will be equal to the input. So our whole layer here will be equivalent to the identity operator. And this property can be very interesting because we can initialize all of our layers here to 0 at the beginning of the training, and we'll see that it will give us more flexibility and better accuracy. So we've said that each layer here, the output of each layer will be the solution of an optimization problem here, depending on previous layers. So we call this optimization problem lower level problem. And after adding here our projection and our lifting and projection layers. We need to, in order to train our model, we need to add another optimization problem here, which will just represent here the minimization of a specific loss between the predicted output and the observed output. And we will call this minimization, this optimization problem, the upper level problem. And so both of these problems will compose what we call a bi-level optimization problem. So by training our neural operators, we are solving this bi-level optimization problem. Now, let's get to some experiments. Basically, we'll try to compare here the Fourier neural operator, the standard Fourier neural operator, with our new architecture, the Bregman Fourier neural operator. And here we will initialize, as we said, all of our Fourier layers to the 0. So we have here the identity operator for each layer. And we will train our models with different simulations of PDEs, for example, advection, burgers, Navier-Stokes, and Darcy, and both in 1 dimension and 2 dimensions. So, for example, here, the Darcy dataset will try to learn the mapping between the porosity to the velocity, the porosity of the material to the velocity field of the fluid. And in Navier-Stokes or burgers, we'll try to map the velocity of the initial time to the velocity at the future time here. And what we see here is that for the standard Fourier neural operators, when we increase the number of layers here, we have a decrease in performance. And this might explain why generally in the literature, they don't exceed 4 layers. However, for our architecture, the Bregman Fourier neural operators, we see that by increasing the number of layers, we are able to observe better performances here. So we are showing some scalability. Our model shows some scalability here. Moreover, we also did the same experiment. I've told you that you could either be the Fourier transform, but we could also use it with the wavelet transform. So we did the same experiment with the wavelet neural operator. So we compared the standard model with our model, and we observed the same type of results here. So we have for a model an increase of performance when we increase the number of layers, and for this standard one, we can see that especially for 32 and 64 layers, this model is not able to learn at all. You can see that specifically we have some exploding gradients problem. Even with gradient leveling, we are not able to train this model properly. Another interesting thing that we observe is when we try to compare the weight distribution of these models. So for the standard Fourier neural operator, you can see that we basically have a Gaussian distribution of the weights. However, for our model, we see that we have a lot of parameters here near 0, and we have some kind of Laplacian distribution. And we think that because of this distribution, we have, even if we didn't really impose the sparsity, we have some natural sparsity in our model, which is why when we increase the number of layers, we still have this flexibility and this increase of performance. So to sum up, we have developed a framework where we view the training of a neural operator as a bi-level optimization problem. And from this framework, we have created a new type of neural operators called Bregman neural operators, which shows some very interesting property and specifically scalability performances. So in the future, we have a lot of perspective, but one of them could be to add some physics-informed loss, as Mr. Seban said. The idea is that we want to learn a PDE. So here, what we did for the standard neural operators, we actually don't really learn a PDE. We just learn a mapping. But if we want to impose some constraint and we want to that our solution is closer to a PDE, we could add here physics-informed loss, which will try to constrain the model to follow the PDE. And we could also modify lower level problem. For example, if here, instead of just applying the divergence and the regularization, we here apply our operator here, U, in our divergence and our regularization, we see that also we are able to create new type of architecture. So the idea is that we might be able to find new architecture which specifically designed for some specific task. For example, if we know that we have a divergence that works very well for a specific problem, maybe with this optimization problem, we'd be able to find which model suit and would be able to learn the best from this problem. Thank you very much.
Questions? Thank you for the. So my question is about the sparse.
So yeah, so in here is just one of the property that we observed. We didn't really wanted it. It's these kind of happy accidents. It's just, I think that because we initialize here, just go back to the architecture, it's here. So we said that when here our layers are equal to 0, we are able to find the identity operator. And if let's say that we have just the standard model, so we don't have this branch. So if we want this layer to be equal to the identity, we'll need to find the correct coefficient here in RT and WT to have the exact identity at the output. And it's really not easy to learn that. So in our model, if we want our layer to be equal to the identity, it's easy. We just need to have our coefficients equal to 0. So I think that because of this skip connection here, our model, if, for example, let's say it doesn't need, it just only need 5 or 6 layers, it will just have to put this coefficient to 0, and then the whole layer will be equal to the identity. So I don't know if it's clear enough. So for our model, it's easier to have the identity operator here, but for the standard model, because we don't have this branch, it's much harder to have the identity operator. So if our model has just too many layers, then it will be hard for him to balance. But for our model, it's more, let's say, more natural. That's, I think, one of the explanations. It's interesting. Good. So here, the regularization is only on our optimization framework. In the training, we don't have any regularization. So in here, that's why I said it's a happy accident, because we didn't even impose some regularization on the coefficient. We just trained it very simply, and naturally, our model has a lot of parameters near 0. So without any regularization, I think even if we added regularization, we would have even more maybe exacerbated the behavior.
The depth.
I think for the Fourier neural operators, it's 8 layers, and for so I took the best models. The best model for the Fourier, I think it was 8 layers, and the Bregman it was 32. Yeah.
Depth. Depth. Learning and identity.
Yes.
I understood your explanation.
Yeah, maybe something to maybe change the perspective. Because we have this property, we don't have to worry how many layers we want. For the standard one, we know that if we have too many layers, we will have a decrease in performance. But for our model, we could add as many layers as we want. The model would find a number of layers, best number of layers necessary. And that's one of the also one of the perspectives. So maybe starting to have maybe a 4-layer model and add some, or do the inverse, so have a lot of layers and then removing one by one to find maybe the best number of layers for each model. And because we have this property, we can do that quite easily.
Perspectives. Searching German class for two priors. So it's like a Pinot-like
Exactly.
Bregman or operators. Do you think do you think that's too able to that include insert your knowledge? So in this case you have 2 different branches.
Yeah.
One with data, another one which is based.
Yeah.
Do you have intuition that it's too able to
Find some hard constraints, you mean?
Yeah, to deal with both data and physical knowledge. It's a tricky question.
Yeah, I'm not sure if I understand it well. So you want to have a loss only in the Fourier domain?
Yeah.
Okay. And
Everything is learning.
okay, but how learn the other branch then?
Up to this.
Okay, so maybe we have a global loss. We just want to minimize some loss between the predicted and target, but we also have some physical knowledge, but this physical knowledge is only applied in the Fourier domain. So good question.
You have no answer. It's okay.
I don't have. I mean, maybe just feeling the loss in the Fourier domain. I'm not sure if that really answers the problem, but so I'm not sure if it's
because
so
everything is much simpler in the Fourier domain while trying to satisfy partial derivatives.
Yeah, but so I think the pins, some pins and some some physics-informed neural networks, and even the Pinot sometimes, because it's another subject, physics-informed. So because the physics-informed neural network or physics-informed neural operators will take advantage of the automatic differentiation property of the neural networks in order to compute the derivatives. Because in partial differential equation, you have derivatives, we need to compute them. And we are, because on how the neural networks is designed, we are able to compute the exact derivative using automatic differentiation. And in some cases, instead of using automatic differentiation, they just used a Fourier transform to compute the derivative. It's easier way, but it's less exact because you need to have some periodicity and things like that. So it's not exactly following the PD. Exactly, it is exact.
Yeah. So as
Yeah, no, T and T plus one is just a layer notation. So here we said that we have a succession here of operator layers. So T and T plus one is just the new representation. It can represent future time, but it's not really clear because we just want, for example, if we have the porosity as the input and velocity at the output, it's different functions. So it doesn't really represent future time.
So one of the start.
Yeah.
So here then perhaps say style or steps.
Oh, it's two different. We have a lot of ways to train them. So technically, if we want to be precise, if we don't use the physics informed model, actually don't learn the PDE. We just learn a mapping. This mapping corresponds to some PDE, but we don't learn the PDE technically because we don't have any information on the PDE. Expect this mapping. And so, sorry, you said. Again, sorry.
Okay. No, but what do you mean by learning compared to learning weapons? So
Yeah, but the PDE is more general than mapping here. So, for example, we could because we have a limited data set, we are able to only learn the let's say the space represented by our data set. But if we add the physics form, so if we add some constraint to be close to the PDE, we have a way more generalizable model. So it's more general when we add the PDE than just here learning the input-output function.
complete the answer, physics information modeling, there are models like hints, physics informed networks. So you know the PDE, you want to learn a surrogate cycle. So you look on that, your PDE solution, and at the end of the day, you get a model in between X, Y, Z, and T, and get the solution that is. So you are solving the PDE, but you don't have any analytical expression, just learn the dynamics. And there is another bunch of work which try to learn the analytical expression. From the dictionary of partial derivatives, what you want is to at least recover or discover you describing the underlying things. Exactly. Or you just have a partial PDE and you have also some observed data. You can learn an hybrid model where each compensates for the limit of the data. You can adapt the learn well the coefficient. You can also suppose the routine where we want to learn the coefficient of the derivative. We don't know the fraction.
Maybe just the way to view that is that basically we're doing an interpolation. So we interpolate something, and with just simple neural operators or neural networks, don't have any idea if our interpolation makes any sense physically. We just are minimizing some kind of loss. But when we add the PDE, we are trying to make some interpolation that minimize some loss, but also that makes some sense physically in terms of respecting the PDE. So that's why it's another thing. Yeah.
Just why did you stop at 64 layers? Is it or
You could have added the so it's just the idea was just to show scalability. I think it depends. It depends on the dataset, but for some dataset, you could add more layers. But I'm not sure that the gain would be really interesting because, as you can see, we have some gain, but we have less and less performance increase. So at some point, it's not really interesting. The idea was just to prove that we gain some performances, but might maybe can be interesting to add some layers. But I think at this point, it's not really interesting because, as I've said, standard ones just use 4 layers. So from 4 to 64 is already a big leap. So maybe we don't need that much more layers.
okay.
Regularization symbol with escape connection.
Sigma -1 here.
Yes.
Yeah.
So you should get PBM message.
So it because so in ResNet we don't have here the inverse of activation operator. We just have a skip connection here from the input to the output, and we have actually tried. I haven't. I don't have this on this presentation, but we actually tried to change this skip into no sigma -1, but just the skip from the input to the output, and we see that we don't see the increase in performance that we see when we use this sigma -1. So it's very even if it's similar in the results, we see different results from ResNet here or ResNet stipulations. Thank you again.
You can thank again the speaker. Thank you.